Vishnu currently studying in Sri Venkateswara College of Engineering, branch CSE. Today I am going to talk about the topic Banker's algorithm for deadlock avoidance. First, let us come to the introduction to Banker's algorithm for deadlock avoidance. The Banker's algorithm is a deadlock avoidance algorithm used in operating system to prevent deadlocks in a system with multiple processes and resources. It was developed by EDSGER DIJK in 1965 and is based on the principle of avoiding unsafe states in the system. The algorithm works by considering the current state of the system and the future resource requests of processes to ensure that deadlock does not occur. Deadlock avoidance. The algorithm is simply to ensure that the system will always remain in safe state. Therefore, if a process requests a resource that is currently available, it may still have to wait. Thus, resource utilization may be lower. Now let us come to the key components of the Banker's algorithm. The Banker's algorithm requires information about the total number of resources in the system and the maximum number of resources that each process may request. It also needs to know the current allocation of resources to each process and the remaining available resources in the system. By analyzing these components, the algorithm can determine if a process can safely request additional resources without causing a deadlock. As you can see, Banker's algorithm example given beside. Now let us come to the understanding safe and unsafe states in the system. In the context of Banker's algorithm, a state is considered safe if there is a sequence of resource allocation that allows all processes to complete their execution without deadlock. A state is unsafe if the system reaches a point where a process cannot proceed without requesting additional resources, which may lead to a deadlock. The Banker's algorithm aims to ensure that the system always remains in a safe state by carefully managing resource allocations. How the Banker's algorithm works. The Banker's algorithm uses a series of checks to determine if granting a resource request will lead to a safe state. It first simulates the allocation of the requested resources to the process and checks if the resulting state is safe. If the state remains safe, the resources are granted to the process. Otherwise, the request is denied to prevent a potential deadlock. Banker's algorithm assign credit limits to each other, reject any request that leads to a dangerous state. In practice, this means the system must keep resource usage well below capacity to maintain a reserve surplus. Banker's algorithm data structures. The Banker's algorithm uses several data structures including the allocation matrix, the maximum matrix, the need matrix, and the available weight. The allocation matrix tracks the resources currently allocated to each process. The maximum matrix specifies the maximum resource that each process may request. The need matrix calculates the remaining resources that each process needs to complete its execution. Banker's algorithm safety check. The safety check in the Banker's algorithm involves simulating the allocation of resources to processes to determine if the system remains in a safe state. The algorithm checks if there is a sequence of resource allocations that allows all processes to complete their execution without deadlock. If such a sequence exists, the system is considered safe and the resource requests can be granted. Banker's algorithm example is given beside, you can refer that. Banker's algorithm safety check example. Consider a system with three processes P1, P2 and P3 and three resource types A, B, C. The current state of the system is represented by the allocation matrix, maximum matrix, and available vector. By performing the safety check, the banker's algorithm can determine if a resource request from a process will lead to a safe state or a potential deadlock. Banker's algorithm resources request evaluation. When a process requests additional resources, the banker's algorithm evaluates the request to determine if it can be granted without compromising system safety. The algorithm considers the requested resources, the current allocation, the maximum request, and the available resource to make a decision. If granting the request maintains the system in a safe state, the resources are allocated. Otherwise, the request is denied. Banker's algorithm resource request evaluation example. Suppose process P2 requests 2 units of resource type B. The algorithm checks if granting this request will lead to a safe state by simulating the allocation and assessing the system's overall resources availability. If the system remains safe after granting the request, the resources are allocated to process P2. Otherwise, the request is denied. Banker's algorithm advantages. The banker's algorithm is effective in preventing deadlock by carefully managing resource allocations. It provides a systematic approach to evaluating resource requests and ensuring that the system remains in a safe state. The algorithm can be implemented efficiently and is widely used in operating system to avoid deadlocks. Banker algorithm limitations. The banker's algorithm requires accurate information about resource allocation and requests, which may be challenging to obtain in real time systems. It may lead to resource underutilization as processes may be denied resource requests to maintain system safely. The algorithm's complexity increases with the number of processes and resources in the system, impacting its scalability. Real world application of Banker's algorithm. The Banker's algorithm is commonly used in multi user operating systems to manage resource allocation and prevent deadlocks. It is employed in systems where multiple processes compete for shared